Alright, so here's an example, this is actually taken from Wikipedia, about the integral of a vector field over a surface. So here's the vector field, it's 2x comma y squared comma z squared, and we want to integrate over the surface the whole unit sphere centered at the origin. Okay, so the surface isn't bad, except once we start doing it, what we're going to need to do is we're going to need to parametrize the surface in two variables. So we're going to need our spherical coordinates. Let's see, that was like sine phi cosine theta, comma cosine phi, or no, sine phi sine theta, comma cosine phi. And now we're going to need to put those into the vector field. We're going to need to find the, like there's r, we're going to need to find r phi and r theta. We're going to need to take a cross product, and then the integral we end up with might still be ugly. So maybe we don't want to do all that work. Maybe instead, this is certainly continuously, or has continuous partial derivatives in and around the sphere, and actually everywhere in 3 space. The sphere is bounded. It's closed. The boundary surface of the sphere is certainly piecewise smooth. It's actually completely smooth. So we can use the divergence theorem. So we're going to say the integral over the surface of S is actually equal to the triple integral of E, where E is the inside of the unit sphere, of div F over the inside of the unit sphere. Okay, well div F is actually not too bad to calculate then. Let's see, so we've got 2 plus 2y plus 2z. Okay, that's nice. And then actually maybe we'll take out a 2. So we're integrating over the sphere 1 plus y plus z dv. Okay, 1 is easy to integrate. Y and z integrated over the sphere, we can do it. It might still actually be a little hard, but let's just think about it, because you are allowed to be clever in these problems. So if we're integrating over the unit sphere, the inside of the unit sphere, so x squared, or so we'll call it the unit ball, I guess, to be consistent. Ball usually means inside, sphere means surface. Integrating over that of y, let's think about the y coordinate, or yeah, the y coordinates on the unit sphere. We've got positive ones over here, and then negative ones over here. I did the wrong sides. That's maybe x coordinates. So, let's see, what's y coordinates? Positive ones over in the back of the sphere, I guess, and then negative ones in the forward, at least with this orientation of the axes. So we expect this integral to be 0. Right? It's completely symmetrical about the y-axis. And then same thing with z. Unit ball. If we integrate, let's see, we've got the unit sphere again. We've got positive stuff up here for z and negative stuff down here, and it's all the same stuff. So we expect this also to be 0. Okay, so then, if we know those things, then the integrals of both of those are 0. So now we just have 2 times the integral over the unit ball of 1 dv, which is really just the volume of the unit ball. And so I'm totally for cheating in this case. We know the volume of a sphere is 4/3 pi r cubed. In this case, r is 1. So the answer should be 8/3 pi. And we actually haven't evaluated a single integral, which I think is 100% okay. And that was an easy way to simplify this surface integral, which is going to be really ugly with phis and thickness.